All right, so let's go ahead and let's start trying some optimization stuff here. Let's say we were told that a box with an open top and a square base is to be constructed of two materials. The bottom, which again is that base, is metal that costs $8 a square foot, and the material for the four sides is wood that costs $2 a square foot. What dimensions will maximize the volume of the box if the material cost of the materials is to be $96? All right. Now listen, I realize it sounds just insanely convoluted, but let's break it down to steps. All right. Step number one, you always want to get what's called your. We oftentimes use the terms here: your primary function and your constraint. Okay. Now your primary function is the thing that you're trying to either maximize or minimize, and the question really should tell us. So if you read it again, you're going to see what is the thing we are trying to either maximize or minimize. Well, if you read carefully, I believe it says we're trying to what? Maximize the volume, right guys? Maximize the volume. So since we're maximizing the volume, I guess that the primary function is going to be my volume. Now what's the volume of the box look like? Well, maybe if we draw the box, we'll get a better answer. So let's take a look at that, okay? So the box looks like this. Here's X, right? Because it does say it has a square base, so I'll say that. And now what I don't know though is how tall it is, yes? So what I'll do is I'll call this bad boy y, okay? So it's x by x on the bottom, but then y on top, all right? So the volume is going to be what? X squared y. So think about it. If you want to find a max or min of something, what do you do? Take the derivative of that something and set it equal to 0, right? Easy enough. You see, but we can't do that because we can't take the derivative of this thing and set it equal to 0 right now. It's got x's and y's and crap in there. So what we need to do is figure out a way to get rid of one of those. Probably get rid of y if you look at that, right? Getting rid of x squared may be tough, but getting rid of y might be easy. And so the thing we use to get rid of y is going to be what's called the constraint. The constraint is the thing which just is. Now let's think about that, right? We know that the surface area of this box is what? Well, it says it's a square base, right? So it's going to be x by x, so I'll call it x squared for the bottom part. Plus, there's no top. If there was a top, by the way, I would do 2x squares, right? There's x squared on bottom, x squared on top. But there's no top, so you got to kind of think a little bit more creatively and say, all right, it's going to be x times y are the remaining four sides, right? If you think about that, there's one, like a shoebox, right? The bottom is x by x. The other 1, 2, 3, 4 sides surrounding it are going to each be of x times y, and so that's 4xy, yes? Now, it didn't tell us what the surface area was going to be. It told us what the cost was going to be. So it did say that what we can do is we can take this function now and kind of turn it, instead of from a surface area function, let's turn it into a cost function. So let's see, cost is what? Well, it says the base is $8 a square foot. So I'm going to do 8 times the x squared, right? Times the base of the box. Plus it's $2 times those 4xy's. And that amount apparently has got to be what? That's going to be 96. And that's the kicker right there. You see, because it's got to be 96, what that allows us to do is solve for one of the variables. So look, I'm going to end up getting this. I'm going to get 8x squared plus, I guess this is what, 8xy. And that's got to equal 96. No two ways around it. So let's go ahead and let's solve for y so we can then take that y and plug it right back in here. So let's see what that looks like. All right. We end up getting 8xy equals 96 minus 8x squared. We're going to subtract 8x squared from both sides, in other words. All right, so let's go ahead and divide by 8x. Divide by 8x. I'll kind of come over here and I'm going to say, all right, apparently y is equal to what? Well, I'm going to take 96, right, and just divide it by 8x. 96 divided by 8x. Now, 96 divided by 8 is 12. So I'm going to make that 12 over x minus 8x squared over 8x is just going to give us good old x, right, because the 8's cancel. And that's nice. So now what I can do is I can take that amount and plug it back in here. So let me update this. Excuse me. The volume is more like this. It's going to be good old x squared times the quantity 12 over x minus x. Do we see that? The volume is going to be x squared times y, but y apparently is 12 over x minus x, right? And so what we're going to end up getting is this. The volume is going to equal it looks as though if you distribute that x squared, that's going to give you 12, just x to the first, minus x cubed. Okay, 12x to the first minus x cubed. Now that's beautiful because now what we can do is we can come down below. Once we basically have our thing we're trying to maximize or minimize in terms of just one variable, right? In other words, there's not x's and y's kind of floating around. There's just going to be a single solitary x. Once that has happened, right, what we can do is step number 2 now is take the derivative of that thing and set it equal to 0. So hold on a second. Let's see. So I'm going to do 12x minus x cubed. So I'll write here the volume in terms of x, which is 12x minus x cubed. I'm going to take its derivative. I'm going to do v prime, and that's going to be what? 12 minus 3x squared. I'm sorry. 12, let's see, 12 minus 2x, excuse me. And I'm going to set that equal to 0. All right? So let's see what this gets us. I'm going to go ahead and, let's think, call it 12 minus everything. Oh, I'm sorry, guys. Excuse me. I think I knew what I was doing there. Excuse me. Probably caught this. This should be 12 minus x cubed. I think I just transcribed it wrong. Give me a second. Yep, my bad. Okay, you probably caught me doing that in my head, which is good. Okay, try that again. Back up. V prime is 12 minus what? Sorry, so that's 3x squared. There we go. And we're going to set that bad boy equal to 0. Okay? Now I'm going to add the 3x squared to both sides, make life kind of easy. So I got 12 equals 3x squared. Divide by 3, and we got ourselves 4 equals what? X squared. Now I know technically that gives us x is plus or minus 2, but this is a box, right? It can't be plus or minus 2. Like, it's just 2, for God's sakes. So I know the dimension is x, apparently. X has got to be 2. So if we go to the diagram, in order to do what? In order to maximize the volume, right? Because we took the derivative of the volume, set equal to 0. Remember, that gives us a max or min. That implies that what? This amount, apparently, in order to do that, that's going to be 2. And of course, so does that. So these two little fellas, both each have to be 2. Now, what's y got to be? Well, luckily, we did the work earlier that y is 12 over x minus x. I'm looking right here. That's y. Wow. So hold on a second. So now I know what y's got to be. That's 12 over x minus x. That's going to give me 12 over 2 minus 2. That's 12 over 2 is 6. 6 minus 2 gives you 4. So apparently if x is 2 and y is 4, we are going to do what? We're going to maximize the volume. Now, if I'm in your shoes right now, I feel there's a little bit of a disconnect. Because I'm like, all right, I get the idea. So step 1, get your thing you're trying to maximize or minimize. In this case, is the volume. Get the thing which just is, which in this case is this cost function we kind of navigated our way through. Solve the cost function for one of the other variables so you can swap it out. And now you don't have x's and y's in your volume. You just got either x or y, whatever you want. And then take the derivative and set it equal to 0. But if I recall, by taking the derivative and set it equal to 0, I get either a max or a min. So how do I know if x equals 2 is a max or min? Well, if I want to, what I can do is I can be tricky here and just get v double prime, right? Take the derivative of this. So v double prime is negative 6x. Do we agree? V double prime is negative 6x. So if I plug in 2, I don't really care about the number itself. I care about its sign, which is that it's negative. If by taking a number that for which the first derivative is 0 and plugging it into the second derivative, we get a negative answer, that implies it's a max. Much the way that if you popped it into the second derivative and got a positive number, that implies it's a min. So it just goes the other direction as it turns out. And this is just like confirmatory, like it's showing us that, yeah, totally, that was a max.